Hello, students. In this video, I am going to go through a lesson on how to graph exponential functions. Let's take a look. You may be wondering, why we need to even know how to graph exponential functions, or why we even need to learn how to graph functions in general. Well, that's because in order for us to truly understand how to work with a function, and in particular work with its inverse, okay, we have to know a little something about how the function behaves. Okay, so suppose I give you this situation here where you're asked to solve 5 is equal to 2 to the x. So leading up to this lesson, okay, we've solved questions that are similar to this. However, this is substantially more challenging. That's because 5 and 2 are not of the same base. Because 5 and 2 are not of the same base, the technique that I've shown you in the previous lessons, they're pretty much obsolete because we won't be able to convert 5 to having a base of 2. So what other methods do we have to actually solve this? Well, we can certainly, try to do a little bit of guess and check and, try to approximate the values, okay? And judging from our understanding of base 2, 2 to the second is 4, and 2 to the third is 8, the answer should be somewhere between 2 and 3, and that would be our a good estimate of what it is. We can also certainly use technology to find out what x is by finding the point of intersection, right? By graphing y equal to 5 and y equal to 2 to the x, and then find a point of intersection. And based on our initial hunch, yeah, that is correct. The point of intersection happens to be at 2.321. But is there an algebraic approach to solving something like this? Well, there absolutely is. Otherwise, I wouldn't be going through this video, right? So there is an algebraic way, okay, for us to solve this, but it will require us to understand the behavior of exponential functions a little more. Okay, so our understanding of exponential functions is this: we have a base, we raise it by a certain value of x, okay, and then from there, our output, okay, is uh, the evaluation of the function at those specified x coordinates, right? And then from that chart, okay, we will then be able to find out what all the y coordinates are, which happens to be 2 to the negative half, negative 2 is 1/4, 2 to negative 1 is 1/2, and so on and so forth. The difference here, though, the problem that I posed to you at the beginning of this lesson is we have 5 is equal to 2 to the x. Well, in this case, okay, in that particular case, right, the input is no longer x. The input is actually the y column. We're looking for a value of x such that when we evaluate the exponential function, we generate 5, right? So technically, right, to say that in a more smooth and logical manner, well, for what values of x will generate an exponential value of 5? 5 is really our input. We're reversing we're reversing what is considered an input and what we are considering an output here. So our input, okay, is actually going to be 5, and our output will therefore be x. So that we can then solve this systematically, right? So what is this? What am I suggesting then? This is actually a prime example of what an inverse function is. So in other words, in order for us to find out the value of x here, we need to know the inverse function. Okay, so with that said, why don't we just get to the inverse function? Well, hold your horses. We can't really find the inverse function yet because we don't really quite understand exponential functions that well as of yet, okay? So because of that, we're going to take a moment and look at how an exponential function behaves. And then after we understand the behavior of exponential functions, we will then proceed to try to understand its inverse a little more. Okay, so that was a really long intro. Now let's actually get to the heart of the lesson. Okay, so we're going to try to understand exponential functions. So to understand exponential functions, okay, let's try to graph these three here. I have y is equal to 2 to the x, 3 to the x, and 4 to the x separately. And let's see what kinds of similarities and differences, okay, you're able to spot. So looking at this, okay, you should be able to see that probably y equal to 4 to the x should be the fastest growing exponential function. So when you graph it, okay, this is the end result of what you should get. 2 to the x is the slowest, quote unquote, right, in growth. 3 to the x is right in the middle, and then 4 to the x is the fastest, and we can see that. So all three of these graphs are experiencing exponential growth. Not only that, there's another similarity between these three graphs. Can you spot what it is? Well, as it turns out, they all have the same y-intercept. Can you see that? They all pass through the y-axis at 0, 1. So all three of these, okay, have a y-intercept of 0, 1, and all three of these are experiencing exponential growth. Why is it that all three of these have the same y-intercept? Well, that's because 2 to the 0th is 1. 3 to the 0th is also 1. Same thing with 4 to the 0th is also 1. Anything to the 0th power is 1. All right, let's try to understand the exponential function a little more. But now, by me adding on other layers, okay, to these exponential functions that we've been working with. See if you can spot some of the similarities and differences between these three. So if you're looking at this and you're saying to yourself, well, I see here that the leading coefficient for the first function is 0.5, and therefore this will cause a vertical compression. You're absolutely right for thinking that. And then the second function has a leading coefficient of 2, which again, that would cause a vertical stretch. You're absolutely right. However, there's something else that I want you to point out, and that is the y-intercept for all three of these are going to change as a result of those numbers out in front. Keep in mind, okay, those numbers out in front, they do cause vertical stretch and compression, okay, just as I had shown you in prior units. However, the emphasis here is that the y-intercepts now are 0.5, 2, and 3, respectively. Now, why are the y-intercepts 0.5, 2, and 3? They happen to be that because to follow the orders of operation, if we substitute in 0, 2 to the 0th is 1. We have to evaluate the exponent before we multiply. So therefore, 2 to the 0th is 1. Multiply that by 0.5, we end up with 0.5. 3 to the 0th is 1. 1 times 2 is 2. 4 to the 0th is 1. 1 times 3 is 3. So if we look at the exponential function in this general form, f of x is equal to a times b to the x, the y-intercept will always be 0, a, and b is our base. Now, with that understanding, let's try to, oh, right, forgot. Again, the emphasis here is the y-intercept, and not so much whether or not there's vertical or stretch or compression happening, okay? All right, now let's take a look at this, okay? How would these graphs change, okay, compared to 2 to the x, 3 to the x, and 4 to the x? In our analysis, okay, I'm going to encourage you to try and re-express 2 to the negative x and compare how that function will behave differently from 2 to the positive x, okay, and so forth. So 2 to the negative x, I can perform a little bit of rewrite. 2 to the negative x is actually the same thing as 1/2 to the x. Why is it 1/2 to the x, you may ask? Well, that's because 2 to the negative x is the same thing as 2 to the negative first raised to the x. 2 to the negative first, last I checked, that is 1/2. And if you look at this, right, now the problem is, or the equation is now 1/2 to the x. So think about this. As x gets larger, so let's say when x is equal to 1, right, y will equal to 1/2. What happens when x is 2? y will evaluate to 1/4. When x is 3, y will evaluate to 1/8. As x gets larger, y is going to get smaller. And this is generally going to be true when we're dealing with a base that's below 1 but greater than 0. Anytime you have a base that's below 1 but greater than 0, okay, the exponential function is going to behave in this very similar manner, where as x gets larger, the y coordinates are going to get smaller. So with that understanding, 3 to the negative x has a very similar analysis. This becomes 1/3 to the x. The base is now between 0 and 1, so therefore x is going to get larger and y is going to get smaller, right? As x gets larger, y will get smaller. Similar analysis for 4 to the negative x, y is equal to 1/4 to the x. The base again is between 0 and 1. As x gets larger, y will also get smaller. So all three of these, okay, as x gets larger, y gets smaller. This is a decaying phenomenon. So all three of these are experiencing exponential decay. Something else I want you to take a look at, right? So looking at the graphs, okay, though all three graphs are decaying, do you think that the exponential functions will pass the x-axis at any point? And why not? Why or why not? If you're thinking that 2 to the x will never ever dip below 0, nor with 3 to the negative x, nor with 4 to the negative x, you're absolutely right. That is because anytime you are evaluating an exponential equation, right? If you raise 2 by any power, positive or negative, it will never dip below 0. We can get very, very, very close to 0. So for instance, 2 to the negative, let's say 100, right? We'll get very, 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 very close to 0, but never ever quite there. In math, we characterize this kind of behavior as an asymptote. The exponential function is approaching a horizontal asymptote, or y, in this case, the horizontal asymptote is y equal to 0. And what an asymptote is, it's simply an invisible line that the function will never ever quite reach. Was there a horizontal asymptote when we were dealing with an exponential function that was growing? Absolutely. As x gets larger in a negative direction, the y's are going to get smaller. So there, in fact, was a horizontal asymptote. It's just that it wasn't as obvious to point out when we were, talking about exponential growth. But there is a horizontal asymptote for those as well. And again, it's at y equal to 0. Okay, so let's now, with that understanding of growth and decay, okay, and what causes growth and decay, let's see if we can figure out whether or not these three exponential functions will grow or decay. Remember, the key feature is if the base is between 0 and 1, it will decay. If the base is greater than 1, it will grow. Let's see what will happen. So for the first one, I have 2 times 4 to the negative 3x. This is the same thing as 2 times 1 over 2 to the 2 to the positive 3. And 1 over 2 to the positive 3 is 1/8, and that is between 0 and 1. Therefore, as x gets larger, y will get smaller, and that is a decaying phenomenon. For y is equal to 2 times 3 to the negative 0.5x, this is the same thing as 2 times 1 over 3 to the 0.5 raised to the x. And 1 over 3 to the 0.5 is, in fact, below 1, but greater than 0. So yes, this is also going to be decay. What about 4 to the negative x? 2 times 4 to the negative x. That leading coefficient had no impact on whether or not the graph is going to be growth or decay at all. So therefore, this is still going to be decay because 1/4 is below 1, but greater than 0. All three of these will be decaying. Let's try to predict what will happen for these three. We're upping the ante a little bit here, right? The questions are getting a little more advanced, a little more challenging, but we're going to make very similar analysis. So here in this case, 2 times 2/3 to the 2x. This is the same thing as 2 over 4/9 x, right? And 4/9 is between 0 and 1. This is going to be decay. 2 times 4 to the negative 0.1 x. This is going to be the same thing as 1 over 4 to the 0.1. 1 over 4 to the 0.1 is going to be below 1, but greater than 0. This is again going to be decay. Not every one of these are going to be decay, because if we check out the last one here, 2 to the 2/3 raised to the negative 0.5x, right? This is the same thing as 2 times 3/2 to the 0.5. That's because when we take a negative exponent, that's the same thing as taking the reciprocal of that exponent. And 3/2 to the 0.5, that is going to be greater than 1. Because of this, this will, as x gets larger, y is going to get larger. The last one here will be growth. Let's try to summarize our findings for the function f of x is equal to ab to the rx. Notice now I added in another value for r here, right, in the exponent. That's because we can certainly change up the values of x, whether or not, we have a coefficient next to it or not. So based on our observation here, right, for the function f of x is equal to a times b to the rx, if the base happens to be below 1 but greater than 0, where r is also greater than 0, then f of x is going to be an exponential decay. If b happens to be greater than 1, where r is also less than 0, this is also going to be exponential decay. If b is greater than 1, but r is greater than 0, this is going to be exponential growth. B is between 0 and 1, but r is less than 0. This is also going to be exponential growth. That's what's the last example that we saw. For this general exponential function, the y-intercept is always going to be 0, a, where b is the base, and the horizontal asymptote will be at 0. Let's not forget about domain and range, right? We can substitute in any values of x into the exponential function here, so therefore the domain is all real numbers. However, for the range, because the exponential function will never evaluate to anything below 0, the range will be y is greater than 0, since anything raised by an exponent can never, ever be below 0. Now, looking at all this information here that's highlighted in yellow can be very intimidating, right? There's a lot of information here. I don't recommend that you memorize these scenarios, these situations, but instead I recommend you go back and perform this kind of analysis, okay, to determine whether or not the exponential function will grow or decay. Do not attempt to memorize these facts here, okay? Although that is ultimately what will happen, okay, if you perform the analysis like I did over here. Right? But looking at this for what it is, okay, it can be very intimidating, so don't memorize this.